Good day to you. All right, we are still on our series on solving questions on elasticity as it has to do with Hooke's law and elastic energy. If you have not seen our previous video on this topic, a question under elasticity, please do well to visit the channel, do well to visit this page for the previous question we solved under this. All right, so we'll continue to another beautiful question here. It says a spring of natural length 30 centimeters, that's 30.0 centimeters, and a force constant of 20 newtons per meter is compressed to 20.0 centimeters. Calculate the energy stored in the spring. So we'll quickly obtain a solution for this particular question. We proceed by listing out all parameters. It is very important that all parameters are listed in every question. All right, so our natural length, I'm going to represent that with the letter L. It's given to us as 30.0 centimeters, which is equivalent, when I divide by 100, equivalent to 0.3 meters. Okay, and force constant 20 newtons per meter. So my K value here is 20 newtons per meter. It is compressed to 20.0 centimeters. Here is where most students used to make the mistake. We assume that this compressed length is the compression or the extension. No, it is compressed to 20.0 centimeters. This is not the new length. Okay, the extension is just the difference between the initial length, that's the natural length, and this new length. Most students will take this value as the compression or the extension, which is wrong. All right, so this value here is L1, that's the new length after the force was applied, and it's given to us as 20.0 centimeters, which is equivalent to 0.2 meters. Okay, now we are told to calculate the energy stored in the spring. The energy stored in the spring is not known, but we know that energy stored in an elastic spring is equal to the work done in that same spring, and that is equal to 1/2 kx squared. All right, 1/2 kx squared. So it means that there is every need for us to now calculate the amount of compression that was produced in the material. The amount of compression that was produced in the material. If a material's natural length is lower than its new length, it is called extension. But if the material's new length, or should I say, if the material's natural length is greater than its new length, it means this is what? Compression. So this is a compressional case. All right, so my compression, which is x here now, my compression, which is x, is simply the difference between the natural length L minus the new length. So my compression is simply 0.3 minus 0.2, and that will give me a compression of 0.1 meters. Okay, so having obtained this compression, it is now more of the work is already done. So the energy is 1/2 kx squared, like I mentioned earlier. E, therefore, which is for energy, will be equals 1/2 times the force constant given, that is 20 newtons per meter, times the squared of 0.1. Okay, so this would be energy will be equals 10 times 0. This will give me 0.01. Okay, so if I multiply this, I'm going to get 0.1 joules. Okay, so the energy stored in this spring when this amount of compression was produced is given to us as 0.1 joules. I want to believe this was very helpful. All right, and if this is helpful in any way, please do it to drop a like, a follow, and comment if this was helpful. Thank you very much. I will see you in our next video.